Yes.
Hey, folks.
Hello, Dr. Kelly.
Hi.
Good morning.
Thank
Hi.
you.
Nice to see you. And thank you for accepting the invitation. The kids are really excited.
Good.
And I'm pretty sure that they will get all the answers to their questions on James Webb Telescope. So thank you very much for joining. So for students who are not familiar with Dr. Kelly, she is an education and outreach scientist of Office of Public Outreach Space Telescope Science Institute, Maryland, USA, right? So here she is, and she's gonna deliver a presentation on James Webb Space Telescope. And before we do, I would also like to take this moment to thank Knoxville Institute for organizing this wonderful webinar for all the kids and for the kids who are not still a part of Knoxville Institute. So it's a really good opportunity for each and every one of us. And I would also like to thank Miss Wendy Pereira for organizing this event. She was the one who was behind it. So she was working really hard to get this webinar up and running. And if it's all right, so we'll take 1 minute of silence in solidarity with those who lost their lives in the tragic Texas shooting in USA, right? So let's observe 1 minute silence, everyone. All right, thank you very much. Over to you, Dr. Kelly. You may proceed.
Okay, great. So thank you very much. I'm going to share my screen here so you can see my slides. Great. So thank you for that lovely gesture. Thank you for the nice introduction. And I'm really excited to be able to talk to all of you. It's the morning right now in Maryland. It's the evening where you are. And today what we're going to be talking about is NASA's next big flagship observatory, the James Webb Space Telescope. My name is Dr. Kelly Lepo. I'm an education and outreach scientist at the Space Telescope Science Institute in Maryland in the United States. And the Space Telescope Science Institute is the home of the Hubble Space Telescope, and it's also the home of the James Webb Space Telescope. So a couple floors right above my office, there are people who right now are telling the James Webb Space Telescope what to do, which is pretty cool. It's a really fantastic place to work, and I'm so lucky to be able to work there. So what are we going to talk about today? We'll talk about Webb's journey to space. We'll talk about infrared light. Infrared is a type of light, and we'll talk about why we want to study infrared light. We'll talk about the science that Webb will be able to do. We'll talk about the telescope itself, and we'll talk about what we are doing right now to get Webb ready to do science. So I first got interested in astronomy when I was about your age. And so I thought it would be interesting to just show you, I show this this graphic to lots of different students when I talk to them about how do you become an astronomer? Because I certainly didn't know that when I was your age. So in order to become an astronomer, you basically have to do all of the school. So you'll finish your everything up to high school, so your last year of school, and then you'll go to a university. And when you're in university, usually you study something like physics, or sometimes universities offer programs in astronomy, but most people just study physics as an undergraduate. In the United States, that usually takes 4 years. It depends on which country you're in. I lived in Canada for a while, and sometimes it took 3 years to finish a degree in physics. And then after that, you have to go on and do even more school. So you do a master's degree, and then you do a PhD degree. And that's where you really get all of the training you need to do to be a scientist. And sometimes you have to go abroad to do this. I mean, that's what I did. I went to Canada to do my PhD. I could have done it in the United States. I've also worked a lot with African students, and often they will go to universities in different countries in order to study astronomy to become a PhD. So after that, you can call yourself a doctor. That's why I call myself Dr. Kelly Lepo, because I have a doctorate in astronomy. And then after that, you'll have what's called a postdoctoral fellowship, where you do a lot of research in astronomy. And then after that, you become a professor. And that's really a permanent job in astronomy. So that is how you become an astronomy professor. That's how you become an astronomer. It's lots of school, but if you like school like I did, then it's a really great career path. So what did my career path look like? So I was born here. This is a map of North America and the United States. I was born in a place called Erie, Pennsylvania. It's on a really, really big lake called Lake Erie. The lake is so big that it has tides, and it's all full of shipwrecks. So I grew up there, and there was a local university where there was one professor who taught astronomy. And I used to go to presentations just like this and learn about all of the cool things that were happening in astronomy in the 1990s. With the Hubble Space Telescope, it just launched then, so it was new and exciting. So for you, it's going to be the Webb telescope. So I grew up in Erie, Pennsylvania. I went to university at the University of Chicago, which is a very prestigious university in the United States. After that, I spent a year living in Europe. I worked at CERN, which is the big particle collider in Europe, where they smash together protons and they found the Higgs boson. After that, I went to Canada to study, and I did a PhD in astronomy and astrophysics at the University of Toronto. Then I taught at different universities, including Gonzaga University, McGill University. Gonzaga University was in the United States. McGill University is in Canada. And then a couple of years ago, I got a job at the Space Telescope Science Institute. And it's my job full-time just to tell people about space and all of the cool science that our space telescopes can do. So this is what our office building looks like. And right on the top floor there is where they control the James Webb Space Telescope. Okay, so that's enough about me. Let's talk about this. This is an artist's picture of the James Webb Space Telescope. So on the morning of December 25th, 2021, Webb launched from an Ariane 5 rocket from the European spaceport near Kourou, French Guiana. So that was Christmas morning for us. I was together with my family. We were in our pajamas, and we all watched the NASA launch broadcast. It was very exciting. And the Ariane 5 rocket was the European contribution to the mission. And because Europe gave NASA this rocket, they were able to have guaranteed time on the telescope. So this is our last view of the telescope as it's leaving the Earth to where it's going to park itself 1.5 million kilometers from the Earth. So you'll see that the telescope is actually pretty compact right now. And that's because Webb is this incredible unfolding telescope. So it had to be very compact so it could fit on the rocket, but then it slowly unfolded itself. So this included separating and tensioning this big sun shield. It's about the size of a tennis court. And then it put down its secondary mirror support. So that's the little mirror that goes in front of the big mirror. And then it unfurled the wings of the primary mirror. That's the big mirror that's made out of 18 hexagon-shaped gold-plated mirrors. And we talk to Webb by something called the Deep Space Network. These are big radio dishes. And so from Baltimore, where I work in Maryland, United States, we send commands to these big telescope, these big radio dishes in California, in Spain, in Australia. And so those are dotted all around the world, so we can always talk to Webb. There's always one big radio dish facing the telescope, and we can tell it what to do. And traveling at the speed of light, commands take about 5 seconds to reach Webb. And then Webb sends information back down, and that takes about 5 seconds as well. So it's about a 10-second round trip. And Webb will download its data twice a day. As I said, Webb is at this very special point called L2. And this very special point follows the Earth as it orbits around the sun. So it completes an orbit in 1 year, just like the Earth does. And this point is 1.5 million kilometers away from the Earth. And this allows the Webb to always be able to talk to the Earth without any problems. And it's also far enough away that it's away from the heat of the Earth and the moon and the sun. And infrared telescopes like Webb have to be very, 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 very cold. And they also have to have very, very, very stable temperatures. And because Webb is so far away from the Earth, it allows it to be very cold, and it allows the temperatures to be very stable. So I just mentioned infrared light. What is infrared light, and why do we want to use it to study space? So here are two different sets of images. On the left are little fuzzy animals called meerkats. And there's also a freshwater crocodile. And the images on the left are taken with visible light. That's the type of light our eyes can see. But if you have a special type of camera, you can take the images on the right. And those are infrared images. And you can see something here. You can see the little bellies of the meerkats. They're glowing very brightly. And that's because you and me and this computer I'm talking into, and anything that's about room temperature glows very brightly in infrared light. And we can tell the meerkats are warm-blooded. They're producing their own heat. And so they're glowing in infrared light. If we look at the crocodile, on the other hand, it's cold-blooded. So it's about the same temperature as the ground. It's not as warm. And we can tell that if we look at these animals with infrared eyes. So there are lots of different types of light, and our eyes can only see a small little sliver of all of the different types of light. And so if you take the different types of light and you line them up by their wavelengths, that's, if you're going up and down, it's the difference between two peaks of the wave. You get what is called the electromagnetic spectrum. That's a big word, so you can use that and impress all of your friends. So this includes gamma rays, X-rays, UV light, visible light, infrared light, microwave light, and radio light. The Hubble Space Telescope you may have heard of before, that sees from a little bit of UV light, mostly visible light, that's the type of light our eyes can see, and just a little bit into the infrared. The James Webb Space Telescope, can see from the red-orange part of infrared light all the way into the middle part of the infrared. And the Spitzer Space Telescope is another scientific successor to Webb, and that just saw infrared light. So infrared light is a type of light that is just slightly redder than what our eyes can see. And the James Webb Space Telescope, NASA's next flagship observatory, is a specialist in infrared light. So why do we want to look at space in infrared light? Well, space is not full of meerkats or crocodiles, but it is full of dust. And when I say dust, I mean stuff that's very similar to the stuff that's in your house. It's like sand or soot in space. And the whole universe is just absolutely full of dust. And so here we have a very famous Hubble image. On the left, we have a visible light picture of what is known as the pillars of creation in the Eagle Nebula. And you see these very dark columns, and these dark columns are all full of dust. And there are baby stars forming inside, but we can't see them because the dust is blocking our view. But if we switch to looking with infrared eyes in the middle here, this is taken with the Hubble Space Telescope using the little bit of infrared vision it has. We can see through that dust, and we can see the baby stars forming inside of these columns. And then if we look to even redder wavelengths, if we look into the mid-infrared, we start to see the dust itself is glowing, just like those meerkats were glowing. So if you want to study dust in space, or if you want to look through dust in space, infrared is the place you want to be. And another cool thing about the universe is that the universe is expanding. The space between galaxies keeps getting bigger and bigger and bigger. And this ends up stretching out any light that is traveling through space. So all telescopes are time machines. And what I mean by that is light takes time to travel. So it takes time for light to go from a galaxy that's very far away to reach us. So we're seeing galaxies and they look like how they were in the past. And as that light travels through the universe, that light gets stretched out. And when it stretches out, it looks redder and redder and redder. So when galaxies emit light at visible light, the type of light our eyes can see, by the time it reaches us, if the galaxies are very, very far away, that light is stretched so much, it appears as infrared light. So that's partially why Webb wants to look at very distant objects with infrared eyes, because if you want to see the furthest things in the universe that we can see, you have to look with infrared eyes. Okay, so that's a little bit about infrared light, the type of light that Webb will look at. Let's see what kind of cool science that Webb can do. So let's talk about galaxies. So this is a picture of a galaxy. It's the Andromeda galaxy. This is a nearby galaxy to us. And you see these beautiful spiral arms in this galaxy. So if you think of a galaxy, usually you picture something like this. So galaxies are collections of stars and gas and dust and dark matter. And they're really they're like a neighborhood or a collection, a city of stars in the universe. So this is a galaxy that's very close to us, to our Milky Way galaxy. It's sort of our sibling galaxy. But if you look very, very far away, galaxies start to look pretty weird. So this in the background is a deep field made by Hubble. And what Hubble did is it pointed at an otherwise dark patch of sky. And it stared at this patch of sky for something like 10 days. And each one of those dots in the background is a galaxy. And they're so far away, they look so tiny, they just look like little tiny dots. But each one of those dots is not a star, it's a galaxy. And I've highlighted the furthest galaxy that Hubble has ever seen here. And we're seeing this galaxy as it was just 400 million years after the Big Bang. This is a very, very old galaxy. And you can see it looks really weird, right? It doesn't look like Andromeda. It looks kind of like a blob, and it looks very red. And so that tells us that galaxies in the early universe are very different from the galaxies that are nearby to us. And so Webb will also be able to look into the ancient universe and see some of the first galaxies that formed after the Big Bang. And we can study them to understand why they look so weird. And then we can study how galaxies change over time. So we can't see the same galaxy changing over time, but we can look at snapshots of galaxies at different distances away from us, which means the light has taken different amounts of time to travel to us, which means we can see different points in history, in the history of the universe. And we can watch as these galaxies turn from these small red blobby things into the beautiful spirals and elliptical galaxies that we see nearby to us. So we can see how galaxies change over time. And Webb will also be able to study black holes. So I don't know if you saw last week, the Event Horizon Telescope released a picture of the black hole at the center of our own galaxy. It's called Sagittarius A star. And this black hole at the center of our galaxy is really massive. It's millions of times the mass of the sun. And we won't get such a sharp picture with Webb because the Event Horizon Telescope combined telescopes together and basically made a telescope the size of the Earth. Webb is much smaller than the Earth, so we won't get such a zoomed in picture. But there's a lot of dust between us and the center of our galaxy where Sagittarius A star lives. So we are going to use Webb to look through that dust. And we're going to look at the stars that are orbiting around the black hole and the clouds of gas that also orbit around the black hole. And we can learn about exactly how much mass, how heavy is the black hole at the center of our galaxy. And we can also look at nearby galaxies. So we can look at the gas orbiting around black holes at the centers of nearby galaxies. And we can look at the massive jets that these black holes blow off, like in this illustration I have here on my slide. And we can see how that influences how stars form inside of those galaxies. And then if we look at the very ancient universe, if we look at the first galaxies to form, we can also look at the first black holes at the centers of those galaxies and understand how those first black holes influenced the first galaxies. So Webb will be able to study how stars are born, how stars live their lives, and how stars die. And so here we have an image of a star forming area known as Mystic Mountain. And we can't see inside of that star forming area because it's full of dust. But if we look with infrared eyes, we can see through that dust and we can understand how stars form inside of these nebulas, these clouds of gas and dust. We can see how normal middle-aged stars live, and we can see how stars are at the end of their lifetimes. So one more thing we can study is molecules. So molecules like water and carbon dioxide. You've heard of them. They tend to wiggle a lot. So if you have two little atoms on your molecules, they tend to wiggle around if you hit them with infrared light, and they absorb some of that light from all of the wiggling. And you can take light from your galaxy and spread it out and see signatures of those wiggling molecules, and you can figure out what your nebula is made out of. So we don't have to take a spaceship there to sample our nebula. We can just look at the light from the nebula and we can figure out what it's made out of. We'll also be able to look at planets in our own solar system. So this is a picture of Jupiter taken in infrared light with a telescope on the ground. Webb will be able to take pictures just like this. We can't point Webb at the sun because it's too hot and it'll fry our telescope. So we can only look outwards. So we'll be able to study Mars and Jupiter and Saturn and Uranus and Neptune and asteroids and comets and Kuiper belt objects. So we'll be able to understand the atmospheres of planets in our own solar system and figure out what all of the small objects in our solar system are made out of and how they move. But it's not just planets in our own solar system. There are also planets around other stars. So one of the stars here is called HR 8799. It's not a very pretty name, but that's the name of this star. And what we've done here is we've placed a black disk in front of the star because the star is very bright. And if you do that, sort of like putting on sunglasses, you can see the very faint planets that are orbiting around this star. So each one of those 4 dots that's moving in this image is a planet. So Webb also has a black disk. It's called a coronagraph. It will be able to block out the light from stars to see planets orbiting around them. And it'll also be able to observe the weather on those planets and their atmospheres. So this is another illustration. It's using our imagination to figure out what planets around other stars would look like. And we can watch planets move in front of their star. And when the planets move in front of their star, some of the light from that planet goes through the atmosphere of the planet, and the atmosphere of the planet absorbs that starlight. And we can use that to figure out what the atmospheres of planets around other stars are like. Do they have atmospheres, or are they just chunks of rock in space? If they have atmospheres, what are the atmospheres made out of? Are they made out of nitrogen like the Earth? Are they made out of carbon dioxide like Mars? Are they made out of hydrogen like Jupiter? We'll be able to figure that out with the Webb telescope. So that's all of the cool science that we'll be able to do. Let's talk about the telescope itself. So Webb is really a feat of engineering. Some very smart engineers worked on this telescope, and they allowed us to do all of the really ambitious science that we want to do. It has specialized optics to control each one of the mirrors. It has detectors that can separate light from hundreds of different objects at the same time. And it also has these thermal control systems to make sure that Webb stays really, really, really cold so we can see the stuff in space and not just the glow from the telescope itself. One of the ways that Webb stays so cold is this big shiny thing on the bottom. So that's called the sun shield. And what it does is it blocks light from the sun and the earth and the moon. And it's able to make, let the telescope to be very, very cold. So on the side that faces the sun, the telescope is 125 degrees. On the side that faces away from the sun, where the mirrors and the instruments are, it's minus 235 degrees. So there's a huge difference in temperature. And that's just to this shiny piece of aluminum coated Kapton. And the mid-infrared instrument has something called a cryocooler. So it's basically a fancy air conditioner. And that, and that helps the mid-infrared instrument stay even colder. That allows the instrument to stay 7 degrees above absolute zero. And if you're keeping track, that's minus 266 degrees Celsius. So really, really, really cold. And Webb needs to be so cold because just like the meerkats, anything that's warm tends to glow in infrared light. So we want to make sure the telescope does not glow in infrared light. So we have to keep it, very, very cold. So Webb's science instruments are on the back. These are the cameras and the spectrographs that take pictures and spectra of stuff in space. There are 3 instruments which look at infrared light that's closest to us, closest to the type of light our eyes can see. It's called near infrared light. And there's one instrument that looks at light that is even further away in the mid-infrared from the light our eyes can see. And Webb has a very, very big mirror. So Hubble has a 2.4 meter mirror. Webb has a 6.6 meter mirror. And the reason that Webb needs a mirror that's so big is because it turns out the redder the wavelength you want to look at, the bigger the mirror you need to have the same level of detail. So Hubble and Webb will take pictures that have the same level of detail, but Webb needs a much bigger mirror to do that. And so I just like to show you this picture. This is a picture of a human at the bottom and the 2 telescopes that I was talking about. The Hubble Space Telescope is the size of a bus, so it's really big. Webb is even bigger than that. It has a mirror that's the size of a 2-story building, so it's enormous. It's 6.6 meters. It is much bigger than any human. But it's in space, so it can be as big as it wants. And one other cool thing that Webb can do is it can take light from an object in space, and it can spread out that light like a rainbow. And as I was talking about before, we can see patterns in that light, and that can tell us about what objects in space are made out of. It can tell us about also about how hot those objects are and how dense those objects are and how those objects are moving. So we have all sorts of clever tricks to figure out lots of different things about objects in space, even if we can't visit them with our spaceships. And one last thing, Webb has an international partnership. So you might hear Webb and you think about NASA, which is from the United States. But there are astronomers all around the world who are going to use the telescope to observe objects in space. And also, the telescope itself was built by 14 different countries in Canada, in the United States, and in Europe. So it's really a worldwide telescope, and all of the pictures that it sends back are free to use from anyone in the world. So it's an international telescope. So in my last couple minutes, let's talk about what Webb has been doing to make sure it's ready to do science. So when we last left off, the telescope had left the Earth, it had unfolded itself, and it had parked itself 1.5 million kilometers away from the Earth. What did it do after that? So all of the images that I'm going to show you now are real images from space. This is real light that has hit the telescope mirrors and gone into the detector, and the telescope has beamed all of this back to Earth so that we can look at it. So initially, when the telescope launched, each one of the mirror segments was acting like its own telescope. So this is an image of one star, and you see 18 dots here, and each dot is from a different mirror. And so what the telescope operators did is they wiggled each one of the mirrors, and they saw which dot moved. And so then they can see which dot corresponds to which mirror segment, and then they can label them. And that's what they did there. And then they took each one of those mirrors and they moved them to make all of the spots in this pattern called a hexagon. So that's a 6-sided shape. And then they focused each one of the mirrors, so each one of the spots gets a lot sharper. And then they moved each one of the mirror segments so that all of the dots are on top of each other. And now each one of the 18 mirror segments is working together to form one big telescope mirror. And this is the result. This is an image of a bright star. taken with the Webb telescope to show that all of the mirrors are aligned. And if you look in the background, what you see a whole bunch of galaxies. And if you zoom in real close, you can see some of them even have little tiny spiral arms. Here's another image that NASA released. This is looking at a whole field of stars with all of the different instruments on Webb. And we can see that it is giving us really pretty, beautiful, sharp images, which is great. So I'm going to zoom in on the MIRI image, the one in the upper right corner. So on the left is the best infrared image we had of this area of space before Webb. This is from the Spitzer telescope. And you can see it's kind of blobby. And then if you look on the right, this is an image of the same area of space with Webb. You see how much sharper the image is. You can see lots more stars in the background. So this tells us that we have a very sharp, focused telescope with a big mirror that's going to let us do lots of science. And these are just test snapshots. The telescope is almost ready for science, but not quite. So what has Webb, the process, so what do we need to do to get Webb ready for science? So we already saw that Webb unfolded itself. It cooled down, so it's very cold because we need a very cold telescope to see infrared light. We aligned the mirrors, so now they're all working together and making very sharp images. And right now we're in the middle of what is called science instrument calibration. So that means that operators are turning on all of the instruments on the telescope and going through all of the different observing modes. And they're seeing, does this work how we think they work? And we're also making sure that we can get all the best science data out of all of those. So they're playing around with it a little bit and making sure it all works and that we understand how it works and that we can do the best science. So we're right in the middle of that now. We should finish sometime in July, and we should have the first beautiful science images coming back to us sometime in mid-July this year. So just in a couple of months, we are going to have some really beautiful science images coming back from Webb. If you want to follow along, there is a website. It's called whereiswebb.com. And you can see the temperature of the telescope right now. And you can also see a checklist of all of the different observing modes that Webb needs to check off to say, yes, this is working. Yes, this is working. Yes, this is working. And when the checklist is complete, then we'll be able to do science. So I hope you are all as excited as I am about the really cool things we're going to learn about space. We're going to learn about the early universe. We're going to learn about how galaxies change over time. We're going to learn about how stars are born, how they live, and how they die. And we're also going to learn about planets, both planets inside of our solar system and planets around other stars. And so with that, I am happy to answer any questions.
Thank you very much for that, Dr. Kelly. It was really informative, and we learned so many things. And the kids are also ready to ask their questions. So students, I request anyone who has any questions to click on the raise hand emoji so that I can unmute you. And please keep your questions short and precise so that Dr. Kelly could answer it easily. Yes, so we have Rohan sir.
Excuse me. You said you in the picture a lot of galaxies, and you have highlighted one of the farthest galaxies, and it looked like this blob. And then again, you showed another slide, the stages of a galaxy, and the first stage is like a glob. So wouldn't it be like it's a new galaxy forming?
Yeah, so what I showed was a zoomed in picture of the farthest galaxy we've ever seen. And it was, yeah, it was one of the first galaxies to ever be born. And it was very, very, very far away. And so it looked kind of blobby and small. And as the over time, little galaxies like that tend to merge together with other little galaxies and form bigger galaxies. And then those galaxies merge with other galaxies and form even bigger galaxies. And so from the whole history of the universe, galaxies keep getting bigger and bigger, and they transform themselves from these tiny little blobs to the big galaxies that we see near us in the present day.
Thank you, Dr. Kelly.
Thank you very much, Dr. Kelly. Next, we have Sudhita.
How does the James Webb Telescope work?
How does the James Webb Telescope work? Well, so light comes in and it hits that big mirror, that big hexagon-shaped gold thing. And then that hits a smaller mirror, the secondary mirror, and then that gets shot into a detector on the back of the telescope. It's like the camera you have on your phone. So it's like a camera on the back of the telescope. And there are electronics that read those images, and then it sends it back to Earth. So it actually works very similar to any telescope that you have on the ground. If you've ever looked through a telescope at the moon or Jupiter or Saturn, it's very similar to that. It's just a lot bigger and a lot more fancy and in space.
Right. Thank you
Thank
very
you.
much, Dr. Kelly. Next, we have Imalka.
How far could the James Webb Telescope could see?
That's a good question. So how far can the telescope see? So it can see back to almost the beginning of time. So the Big Bang happened about 14 billion years ago, and it can see about 100 million years after the Big Bang. So it can see back to when the universe started forming galaxies. So it can see almost as far away as anything can see.
Right. Thank you very
Thank
much,
you.
Dr. Kelly. Next, we got Ayusha.
Excuse me, in which speed is the Hubble telescope going?
Which way is the telescope going? So the telescope sits at a point about 1.5 million kilometers from the Earth. And it just sits there and it looks out into space. And it follows the Earth around as it orbits the sun. And so I think some people think that if you want to take a picture of a galaxy, you have to fly your telescope to that galaxy. But that won't work because galaxies are, thousands or millions of light years away. So it would take 1 million years for your telescope to travel to a galaxy. So that won't work. So so telescopes just sit either on the Earth or in space and look outwards. And the James Webb Space Telescope follows the Earth around as it orbits the sun. And it's there right now. It's in its parking space. It's very happy. It's sending us pictures back.
Thank you very much, Dr. Kelly. Next, we got Arudit.
How far can it see? How far it can see from infrared waves and visible light?
Oh, so how far can it see in infrared light? Let me see if I can share my screen again. And
No, doctor, he said, how far can it see in infrared light and in visible light?
oh, okay, yes. Let me show you. So Webb can see from about the orange and red part of infrared light. So about the same color as its mirrors. So the mirrors are gold colored. So we can see a little bit of visible light. And then it can see all the way about halfway through the infrared spectrum of light into the mid-infrared, which is and the limit is set by the detectors on the telescope and how cold it can get. So the further you want to see in infrared, the colder you have to make your telescope. And so that's about the limit we can see in the infrared, because if you tried to look any farther than that, you'd mostly just see the telescope glowing, even if it is very, very cold.
Okay.
Thank you very much for that, Dr. Kelly. So I guess that's all the questions that we have tonight. So thank you very much for those answers, Dr. Kelly. It was really enlightening, and the kids enjoyed it as well. So then again, I would like to take this opportunity to thank you for joining the webinar and for accepting our invitation. And I'm looking forward to have you with us in the upcoming sessions as well. So
Yes.
thank you very much, Dr. Kelly. I hope you enjoyed this webinar.
Thank you, and keep looking up.
All right. Take care. See you.
Thank you, Dr. Kenny Lepo.
Kids, please stay online. Do not leave the session. Okay, so yeah. So now